Okay, we now have a presentation entitled Biogas Recovery from the Filtrates of Hydrothermally Treated Wet Residue Streams, presented by Dr. Tim Hendricks. Tim has a PhD in environmental engineering and since 2011 has been working at PAC, a Dutch company that is globally active in industrial wastewater and gas treatment, and where Tim is the global lead on anaerobic technologies. So Tim, the floor is yours. Thank you.
Yeah, thank you for that introduction. I indeed work at Parks, and I will briefly introduce Parks so you understand a little bit what kind of company we are. And after that, I will focus indeed on the biogas recovery part of the FQ project. So we are a company that's present worldwide. The head office is in the Netherlands, in a small village called Balk. That's where the company was set up in 1960 already. What's unique about Parks is that we don't only deliver solutions to industry, but we also have developed our own technologies. We have our own R&D department, we have our own production facilities, so we can, and you can see in some of the pictures below, we can go from the whole, let's say, development train from lab research to pilot research to building full-scale installations. And now, since several decades, we also have production facilities and offices in, for instance, China and Brazil. What do we do in our installations? We use, let's say, natural biotechnology to convert wastes. So we do not work with genetically modified organisms or something. We just use the organisms that are present in nature, but we, let's say, pimp it up a bit to make the processes speed up a little bit so that we can design industrial scale installations that are very efficient in converting, for instance, wastes to biogas, but also removing hydrogen sulfide from biogas that is produced. But as you can see in the picture here, we also look at the recovery of nutrients or the removal of nutrients, for instance, phosphorus and ammonium. Now, this is very briefly what we do at Parks, and in this talk I will mostly focus on the biogas part. So how do we produce biogas from the filtrates from the FQ process? So a brief overview of the process itself and where we work on. So yeah, you have seen this TORWASH scheme before. Our part is focusing on the filtrates that are produced from the dewatering step. And what can we do with that in terms of recovering biogas from these filtrates? Now, what will we look at? We'll look at the feasibility of using these filtrates to actually produce biogas, and next to that we also look at, let's say, a case study where we look at what would the full-scale biogas production installation look like for these different residues. And obviously the residues are the paper sludge, the olive pomace and the orange peels. Maybe very briefly first, why would we even want to look at biogas recovery? So these filtrates, they contain all, let's say, the soluble organics, but also nutrients. And if you want to dispose these streams, yeah, you first have to either apply a treatment or you pay a high disposal fee and somebody else does this treatment for you before safe disposal is possible. Now, both are an option, of course, but I hope to show you in this presentation that looking at recovering the biogas is actually a benefit also to the overall FQ process. Now, biological treatment can be done aerobically or anaerobically, very simply said, and anaerobically is by far the more interesting compared to aerobic, because now if you look at the picture on the left-hand side, you see anaerobic treatment. So of all the organics that you convert, you can recover, let's say, 95% as methane, so that's an energy carrier that you could use again, and only a small part is used to produce new anaerobic biomass. If you do the same thing aerobically, so you bring in a lot of air into the process, you roughly convert half of it to CO2. You basically mineralize your organics and you lose all the energy content that is present in it. and you produce a lot of excess biomass. Now, you might think this is interesting because you can put it back into the FQ process, but in a way that's destroying part of your energy because you put it into a new biomass. So more interesting is to look at the anaerobic treatment. Now, and additional advantages are indeed that the conversion anaerobically requires less energy input, but I'll come back to that later. And as you can see in this picture, comparison between anaerobic and aerobic is that the biomass yield anaerobically is much lower. So that means you actually can recover more of the energy rather than putting it into new biomass. Now, just to give you a little bit of background why it is interesting to recover biogas. What do we do on biogas recovery in this project? So basically we received the filtrates from the pilot campaigns from the 3 different substrates, and we tested this at lab scale to see how much biogas can you produce from each of these filtrates. Now we do this under controlled conditions. We put the right anaerobic microorganisms with the substrate. We do it at the right pH. We check on availability of nutrients, micronutrients. We do this obviously in anaerobic conditions and at a temperature that we typically apply in the full-scale process, which is 30-35 degrees. Important to mention here is that we look at the soluble substrates, so the organics that are in soluble form. As you saw in the presentation from Douwe, is that there's a small fraction, even in the filtrates, of solids. We do not look at this substrate because it will require a lot of effort to convert that to methane. And it's only such a small fraction that it is also economically not interesting to also try to treat this fraction to methane. So we really look at the soluble substrate, and that allows us to build a compact process that generates biogas from this filtrate. So we're looking at soluble substrates here. Basically what we do in the test, we put all the reactants together, we put it in ideal conditions, and in time we follow the biogas that is produced in this test, and we let the test run until there's no further biogas production. And what we do then is we measure the soluble substrate concentration at the start and at the end, and that gives you then the insight on how much can be converted anaerobically. Now we used what is called the oxytop setup for this test. Maybe somewhat misleading because oxytop suggests that there's some sort of oxygen input, but the whole idea of this test is that it measures the pressure increase or decrease in a setup. Now, for oxygen consumption, it measures a decrease, but we obviously look at the pressure increase because of biogas production. And I will show you some graphs of the different substrate later. I see the pictures have slightly moved, but so we looked at 5 different filtrates that we received from the pilot testing. 2 from paper sludge, 2 from the olive pomace, and 1 from the orange pomace. And now looking at the COD concentration, so the measure of the amount of organics that is present in the substrate, you see that there's quite some difference between, for instance, paper sludge and the olive pomace and orange pomace. So the paper sludge, as said earlier, it was quite a dilute stream. In addition to the organics, we also look at nutrients, and mainly nitrogen and phosphorus. And why do we look at these? That's because we're working with a biological process to produce the methane. The microorganisms need to grow if they want to convert the organics to methane. And to grow, they need nutrients like nitrogen and phosphorus. Now, we checked for all these substrates, and nitrogen and phosphorus was abundantly available in these substrates. And that is interesting for a full-scale application because it means you do not have to add this to the process, which means that you do not have additional operational costs. So the first check is just, is everything present in the substrate to allow stable conversion of the organics to biogas. Now, that was the case for all these streams. And then with these substrates, we then started our batch test to check what is the biodegradability for the substrate. Like I said, we looked at the 3 different substrates, and here you see a typical picture of the biogas production in time. You see quite some different shape of the curves, but in all cases you see that there's biogas production, and at some point it levels off. which means that there's no further biogas production, and that's the end of the test. What you see in the batch experiment is not necessarily exactly what is happening in the full scale. So here it looks like the olive pomace filtrate is very easily converted, but that also depends on the conditions in the test. In the test you have, let's say, not your biomass 100% optimized to your substrate yet, but in a full scale installation you will, of course, after operation. So the main key message from these is that all these substrates could be converted anaerobically to produce biogas, and of course from the test it follows how much biogas could be produced. And that I summarized in this table. So if you look at the paper sludge, so the anaerobic biodegradability for the two different samples that we tested, they were obtained under slightly different conditions of the TORWASH process and the dewatering step. But the anaerobic biodegradability was a little over 60%, which means that 60% of the organics that were dissolved in the filtrate could be converted to methane. So that's quite good. And if you translate that to the amount of biogas, or maybe easier, the amount of methane that is produced per cubic meter of this filtrate, that is in the order of 2 to 2.5 cubic meters of methane produced per cubic meter of filtrate coming in. So significant amounts of biogas produced. Now, if you look at the olive pomace, there the biodegradability was maybe slightly higher, but still very good. And due to this waste stream being much more concentrated than the paper sludge, if you calculate it back to the amount of methane produced per cube of filtrate, this was higher with 5 to 6 noble cubes of methane per cube of filtrate. Now, and then finally, the olive pomace, it had the highest anaerobic biodegradability, the organics, so 77%. So that's very good. That means that the majority of your organic substrate is converted to methane. And also, this was a very concentrated substrate, which meant that you can produce up to 12 cubic meters of methane per cubic meter of filtrate. So all in all, the anaerobic biodegradability of all these filtrates was good, and it could generate a lot of methane for you to be used elsewhere in the process. And that's the next step we looked at. So what would it look like if you treat these different filtrates at an industrial scale? What kind of anaerobic, how large does your anaerobic insulation need to be? And what does it mean in terms of energy consumed by the process and energy generated in the form of methane? So for that, 3 case studies were defined. So let's say the size of a full-scale project. And that meant for the paper sludge about 2.4 tons per hour of filtrate coming to the anaerobic insulation. For olive pomace, it was just under 50 tons an hour, so quite a bit bigger flow. And for the olive pomace, again a bit lower, 3.4 tons per hour. Also for the filtrate, some assumptions were made in terms of the COD, so the organics concentration in the filtrate. These numbers are slightly different from what I showed you before, but these case studies included some optimizations in terms of dry solids being fed to the TORWASH project process. Now, for us to design a full-scale installation, what we are interested in is the kilograms of organic material per day coming into this anaerobic installation, and that are listed in the column filtrate COD load. So that's just over 5.5 tons of COD for the paper sludge case, 33 tons for the olive pomace case, and 3.7 tons for the orange peel case. Now, the anaerobic biodegradability is basically the averages of what I showed you before for the test that we did. And for the filtrate temperature, in all cases, we assume 35 degrees, because that's, let's say, the optimal temperature for anaerobic treatment. So this is basically the basis of design for the industrial scale design. Then very briefly on what would we use as an anaerobic installation in such a case. What we use is what we call a high rate anaerobic treatment installation. High rate refers to a high conversion capacity per volume of anaerobic reactor. So that means that we treat and produce a lot of biogas per cubic meter of reactor. And that is, of course, interesting because it means you have a smaller reactor, smaller footprint, and still a high biogas production. Now, what is key in such a process is that we apply granular anaerobic biomass, and I showed a picture here in the lower part. This is from a lab scale reactor where obviously you have a glass wall, you can see what's happening inside, but you see a lot of brownish granules, and in between you see the biogas produced. This is typically what's happening in our full-scale installation as well, a dense bed of granular biomass, so high concentrations of active biomass, which convert the organics to methane, and that's the gas bubbles you see. Now, for those interested in anaerobic installations, it's an upflow system, and it's a closed tank because we are producing biogas, so you want to contain this and capture it. In the top of the installation for this technology, we have separation of the gas from the liquid, and in the lower part of the installation, we separate the biomass, these granules that you see in the picture, and keep them inside the reactor so that they can contribute to further conversion. And what comes out is basically the treated effluent, the treated filtrate, which is lower in organics, but does not contain the granular biomass, because that's what we keep inside. Now, I can talk about this for hours because that's our core business, but I suggest if you have more questions that we do that in the break. So let's look at the case for olive pomace filtrate. So as I showed you before, the case study we look at is just under 50 tons of filtrate per hour. So that will be coming in to the anaerobic reactor. And now for this scale of olive pomace flow, we would need just under 1,000 cubic meters of volume of anaerobic reactor. So that's what I put inside the reactor. And what you generate is 6,500 normal cubic meters of methane per day. So a substantial amount of biogas. And if you convert that to amount of kilowatt hours, that's roughly 1,400 kilowatt hours per cubic meter of filtrate. So quite a large amount. So as you can see in this picture, it's not just an anaerobic reactor. You also need pumps there to make sure that the process operates well. We also estimated the energy used by the pumps in this process, and that came to about 0.15 kilowatt hours per cubic meter of filtrate. So that's rather low, and I made a very rough overall energy balance, certainly not into the detail that Marco will present later. But just to give you an idea of that, the energy that you need to put into the process to make it work well is insignificant compared to the amount of energy that you can generate from the biogas. And this net energy production, of course, can then be used elsewhere in the FQ process to make the overall energy balance more favorable for this. So this is very simply said how we would treat the olive pomace filtrate. The filtrate comes in, it's converting the organics to methane, and a very small part of the energy that you generate has to be used in the process itself. Now, if we look at then for the three different cases, for paper sludge, for olive pomace, and for orange pomace, I've listed here the size of the reactor. So for paper sludge, olive pomace, the case studies we looked at, they're smaller. So also the anaerobic reactor is much smaller, only about 200 cubic meters. And the power consumption, now, it's relatively more for a small-scale anaerobic reactor, but still very small compared to the methane production of the whole process. And if you look especially at the net energy output, you see that for the paper sludge, it's about 200 kilowatt hours per cube of filtrate net energy output. And for the other two streams, it's 57 and 120 kilowatt hours per cubic filtrate energy output. So there's a significant amount of energy that you can generate. So I think this clearly exemplifies why it is interesting to treat these filtrates anaerobically, because you reduce, of course, the amount of organics that are still in the water, but you actually do this in a way that you still make best use of the energy content in these filtrates. So the TORWASH process recovers most of the energy to the pellets, to the solid fraction, but still from the soluble fraction you can recover a lot of energy in the form of biogas. Now, just as an example, I showed some pictures here of full-scale installations. So the two on the left, they are probably about 100 to 200 cubic meters. The picture of the two blue reactors, that is very large scale. They're about 2,500 cubic meters each. But just to exemplify that, yes, you can build such big reactors. And the reactor volumes that we calculated for these 3 case studies, they're certainly not strange volumes. Now, then I come to a brief summary of the conclusions for these 3 filtrates. So yes, all filtrates can be treated anaerobically, and they showed a good anaerobic biodegradability, ranging from about 55 to up to 77%, depending on the type of filtrate that was used. Important for full-scale anaerobic conversion is that there's sufficient nutrients present in each of the filtrates. As was also expected, of course, because the whole idea of the TORWASH process that you try to move these to the liquid fraction, and that's favorable for anaerobic conversion because you do not need to add these, and therefore you avoid operational costs. We also looked for each of the filtrates at the design of a full-scale installation, and it also shows clearly that yes, you need to put a little bit of energy in, but you generate so much more that it's definitely, from an energy point of view, a very good idea to recover biogas from these filtrates. And obviously, the excess energy can then be used elsewhere in the FQ process and make sure that, on overall, the energy balance of the whole process also looks positive. So that's in brief what we looked at in the FQ process. I hope it's been clear to you, but if there's any more questions, then feel free. Thank you.
Is there any questions from the floor?
Yes, one small question, because there's quite some difference between the digestibility between the different feeds. Is that because maybe some are more phytotoxic than others, or is it just the maximum conversion? Do you know if it's one of the things that's been clear from the results?
Yeah, no, indeed. So we had to also check indeed if there's some sort of toxicity. We did not see that in any of these streams. If there's real toxicity, what would happen is that the biogas production will just not happen at all. Sometimes you could have indeed some sort of adaptation phase, but let's say purely on the anaerobic biodegradability, we did not see any toxic effects. What you cannot see from such a test, you would have to do a different test, is that maybe there's some compounds that kind of like continuously annoy the anaerobic microorganisms, but that usually you can compensate by just putting more microorganisms in it. So no, so from what we've seen, all the filtrates could well be treated anaerobically.
Sorry. Yep, next question.
So we saw the biogas potential from the 3 streams, and what surprised me is that but correct me if I'm wrong, if that the biosludge has the highest potential.
No. So if you look at the organics that are in the water, it was just over 60% of that could still be converted to biogas. But if you look at, for instance, the orange pumice, then it's 77%.
Yeah, I meant the column that has the per cubic meter centrate. That there is, but there was clearly that the biosludge.
That has also somewhat to do with the definition of the case study. There was a very high solid concentration assumed in the case study, which was different from what we tested in the pilot scale filtrate. Obviously, the more concentrated you make your stream, the more methane you can recover per cubic meter of. So that's a case study, but I think, but correct me if I'm wrong, Heather, I think it still has to be proven that you can actually operate at such high concentration, or that you can even reach this high concentration, let's say, realistically as a feedstock.
But so there's not for the digestion process itself, the biosludge, or it's not a specific reason that is digested better than, for example, the centrate from olive oil or pumice or anything else.
No, and if anything, I would expect indeed that biosludge is less easily converted because some microorganism already grew on it, and typically microorganisms are more difficult to convert to biogas than other organic substrates.
Okay, thank you.
Quick question. You mentioned the requirement of certain minerals like phosphates and nitrogen for the process. Does that mean that in the FQ process overall there's a trade-off between nutrient extraction and biogas production?
Well, not necessarily. I mean, the anaerobic conversion is only a small part is going to new biomass. So for that you need enough nutrients. So there is, let's say, a threshold. You always want to release some of these nutrients, nitrogen, phosphorus. But if it's a lot more, it's not necessarily a problem. But it depends very much on what you do afterwards with the water coming out of the anaerobic reactor. You remove the organics, but you still have the nutrients, minus a little bit that was used for growth. So if you want to recover those nutrients, then it's best just try to get it all into the filtrate. If you do not really know what to do with the water after anaerobic digestion and you do not want the nutrients there, then of course you would prefer to have them in the pellets, provided that they don't create problems there. So a trade-off, there has to be a minimum amount of nutrients present, but I think that's quite easily reached, even at low solubilization of the nutrients.
Thank you. Yeah, that's it. Okay. Thank you, Tim.
Thank you.